So we're talking about the graphs of quadratic functions. So what's a quadratic function, by the way? Well, any function of the form f of x equals ax squared plus bx plus c, where a, b, and c are constants, is a quadratic function. So it's a two-variable quadratic equation, right? In other words, you can always think of the f of x as y and call this y equals ax squared plus bx plus c. So it's a two-variable quadratic equation, and of course then it graphs to be a curve in the xy plane. It doesn't graph to be a line, it graphs to be a curve. So that's what we're looking at today. Goals number one, we want to graph a quadratic function using the standard form of its equation. I'll show you what that is as we go. Goal number two, to find the vertex and axis of symmetry of a quadratic function, whatever that is, whatever those are, I should say. I'll define those in a few minutes. Goal number three, to find the domain, the range, and the maximum or minimum, it has one or the other, of a quadratic function. If you were asked to graph, say, y equals x squared by hand, would that be tough to do? No. So what kind of values could you plot? I would plot x values, right? So by the way, this is the simplest quadratic function you can think of. The simplest quadratic function you could think of. You could almost think of it as the parent of all other quadratic functions. What would be some good x values to plot? 1. 1 is a good one, sure. I'm going to put that a little down the list, though. So we're plotting x values, so 1 would be a good one. How about 0? What about negative numbers? Do you have something against negative numbers? Don't be racist against negative numbers, right? So -1, -2 maybe, and then maybe +2 as well. So that would be a nice selection. And then what does this function say? You can think of it as the parent to all quadratic functions, or you can think of it as the squaring function. In other words, whatever you input into it gets squared. Whatever the input is, remember x stands for the input, whatever the input is, you square it. So what do we get on the right side on that chart that we created? You square -2, what does that become? 4. You square -1? 1. You square 0? 0. You square 1? 1. You square 2? 4. Let me grab a chunk of graph paper. I don't know why I still call it graph paper, because it's not paper. This squaring function is not difficult to graph. I know that 0, 0 is on the graph, so I'll put that on there. I know 1, 1 is on it, -1, 1, 2, 4, 1, 2, 3, 4, -2, 4. And all you do is, once you get a nice selection of points, draw a nice kind of U shape through it, nice smooth curve. It's not a V shape, so I don't like, kind of went a little off track there. It's rounded at that bottom low point, and then rounds back up, and then goes up. We call that shape a parabola. Which leads me to, this might just be the lamest joke that I've told you yet. And I've told you some pretty lame ones, right? Why is 6 afraid of 7, 7, 8, 9? For example, okay, here's maybe the lamest one yet. What do you feed a baby parabola? And you might be able to figure the punchline out. What do you feed a baby parabola? Quadratic formula? Yeah? All right. I told you, the lamest joke, possibly the lamest joke of all time, right? Not just math, any joke. But not hard to graph the most basic parabola, right? The most basic quadratic function, which gives you the picture is called the parabola, the curve is called the parabola, the equation is called quadratic, okay? And it's a degree 2 polynomial equation, it's called quadratic. So, all right, not hard to graph the most basic one, y equals x squared, right? What do you think would happen if I stuck a negative in front of the x squared? So if instead of having y equals x squared, I have y equals -x squared. So let's extend this table a little bit. So the first one was y equals x squared. The first set of output values was for y equals x squared. The next set of output values for y equals negative x squared. But I'm going to use the same inputs. So you almost can't see the negative. Negative x squared. So what do you think is going to happen then? All of those y values are going to become the opposite of what they were, right? So that's all that's going to happen. If you leave that negative outside the x squared, you're going to square everything and take the opposite of it. That's what the negative in front of the squaring function says to do. So instead of 4, you get negative 4 for the output when you plug in negative 2. Instead of 1 for the output when you plug in negative 1, you get negative 1 for the output. 0, well, the opposite of 0 is 0. Opposite of this guy, negative 1. The opposite of this guy, negative 4. And that has the effect of flipping the graph. Visually, it has the effect of flipping the graph upside down, doesn't it? So if I do this one in blue, then 0, 0 is still on the graph of y equals negative x squared, but then 1, negative 1, negative 1, negative 1, 2, negative 4, 1, 2, 3, 4. All of these, so like this point gets reflected over to here, essentially. It's like the x-axis is a mirror, a one-dimensional mirror, and you're reflecting the graph in green across the x-axis when you stick a negative in front of x squared. So at negative 2, you're at negative 1, 2, 3, 4. And then you just graph the smoothest curve you can. It should look like the graph in green upside down, because that's what it is. So that's also called a parabola. And I should mention that we call the low point or the high point, so if it's the graph in green, this guy is the low point. If it's the graph in blue you're looking at, this guy is the high point, right? Either way, we call that the vertex. If we compare the graphs in this example of y equals x squared, y equals 2x squared, and y equals negative 2x squared, okay, a here is 1, a in this one is 2, and a in this one is negative 2. And just graphing them on a calculator real quick, if you graph y equals x squared, it looks like that. Y equals 2x squared, it's the graph in red. And y equals negative 2x squared, it's coming, is the graph in black. Okay, there are two things I want you to get from this picture. So focus on the first two graphs, y equals x squared, the graph in blue, and y equals 2x squared, the graph in red. So a equals 2, how does the graph in blue compare to the graph in red? It's twice as tall. So a equals 2 or a equals anything, it's going to either stretch or shrink out the graph vertically. That's hard to tell. It's tempted to say that the graph in blue is wider than the graph in red, and it appears that way, but really what's happening is it's the height that's being affected. So the graph in red is twice as tall as the graph in blue because you're multiplying essentially the graph in blue times 2. The equation that gives you the graph in blue, the output you're multiplying by 2, so it makes it twice as tall. So it affects the height vertically. That's what A does. That's really what the absolute value of A does. And then if A turns out to be negative, look at the graph in black, then the parabola opens down. And that's true anytime A is negative. That's what I want you to get from this problem.